All right, here we go. Hyperbola, definition. Guess what? Just like all the other ones, the definition of a hyperbola starts out as, okay, so here it is. It's the set of all points P such that the absolute value of the, any ideas? For an ellipse, it was, we did the sum of some distances. Guess what this one is? Difference between the distance from P to two fixed points. Guess what the fixed points are called? Foci. Is constant. So it's the set of all points P such that the absolute value of the difference between the distance from P to two fixed points is always constant. Now this one is not nearly as easy to demonstrate on as the other one. I'm just going to leave it at that. I just wanted you to see that it's still a set of all points. You're just doing a difference this time instead of a sum. Okay? Its standard form is actually very similar to the standard form of an ellipse. But do you remember when we talked about hyperbolas way back at the very beginning? What was the key idea in determining whether or not one of those equations was a hyperbola? The a squared and the b squared, or the a and the b in the general form, had to be different signs, right? So it was subtraction. So here's what your standard form is going to look like. You're going to have x squared over a squared, but instead of plus, guess what? It's going to be minus y squared over b squared, still is equal to 1. But do you think that the x squared always has to be positive? No. So it could be written like this. Y squared over, and it really doesn't matter. If you want to leave b squared with the y squared, that's fine. Minus x squared over a squared is equal to 1. Okay? Now, here's what the difference is. Do you remember what we talked about with hyperbolas, how they were graphed? When you were graphing them back on that first day, they either looked how? Air draw. Yes. Okay, some of you took the easy way and said that they opened left and right. And then the other way is to open, and some of you are getting really good at this, up and down, like this. Yeah, it's not so easy, is it? Okay. Now, here's the thing. Which one is which? If the x squared is the positive, which way does that one open? Is that the sideways or the up and down one? Can this thing have x-intercepts? So if you were to plug 0 in for y, could you get x-intercepts? Could you solve that for x? Yeah, so can it have x-intercepts? Yes, so therefore if it can have x-intercepts, it must open sideways. So when the x squared is first, or I guess it doesn't necessarily have to be first, but it has to be positive. If the x squared term is the positive term, then it's going to be a hyperbola that opens like this. Guess where these 2 points are, this point and this point? No, those aren't the foci. Okay, there you can think of them as the vertices. Where do you think they are based on that equation? At what? Not A and B. Aren't they the same distance away from the origin? Yeah. This is at A and this one's at negative A. Now, those 2 fixed points, those foci, they are also on that same axis. So they are on the x-axis. Do you think they're further away from the origin than A or closer to? further away because of the subtraction property. So they're going to be in here somewhere, but they're also equidistant from the center, from the origin. And guess what this distance right here is called? It's C again, just like before. Now, I think C is a little bit easier to find on the hyperbolas than on the ellipses. Because do you remember with the ellipse, it was C squared equals either A squared minus B squared or B squared minus A squared, whichever one was larger. For a hyperbola, it's a little bit easier, because guess what I get to do with my A squared and my B squared? Add them. So it doesn't matter what order they come in. It's A squared plus B squared this time. The way I remember it is like this. If it's subtraction here, then in my C squared equation, it's addition. Remember with the ellipse, it was addition. In my C squared equation, it was subtraction. Does that make sense? Yeah? Okay. All right. Oh, one more thing I think I wanted to say is that this axis that contains those foci, okay, it's called the transverse axis. And you're going to read that in your book. They're going to refer to the transverse axis. And so if they tell you that the x-axis is the transverse axis, then you know it opens sideways. If they say that the y-axis is the transverse axis, then you know it opens up and down. Okay? So that was going to be my next question. So if the y squared is the positive one, then how is this hyperbola going to open? Up and down. So it's going to look something like this and like this. Guess what these are now? 0, negative b. Guess where the foci are? Up here and down here. I think of them as being on the inside of the little moles, if you will, or the branches. Okay, any questions on that? So let's just take a look at this. So it says to graph this equation and then find the foci. This should look pretty familiar to you, does it? Yeah, because it's just like what? Yeah, wasn't it one of the warm-up? The warm-up, it was, instead of minus, it was plus. Okay? But since it's minus, you know it's going to be a hyperbola. What do you think you're going to want to do first in order to graph this? Divide by 64 because you want it equal to 1. You want it equal to 1 so that you can see your A squared and your B squared. Okay? Because that's going to let you move away from your center point of 0, 0. Okay? Which means we're going to end up with x squared over 4 minus y squared over 16 is equal to 1. Okay? All right. So let's look at graphing this thing. All right. Now, you already know, or you should know, which way this hyperbola is going to open. Is it going to be a sideways parabola or hyperbola or an up and down hyperbola?
Up and down.
Why sideways? Because the x squared is positive, so it's going to be a sideways opening hyperbola. Does everybody agree? Okay. Which means your x-intercepts are going to be where and where? 2 and negative 2. So here. Now, you have a general idea of what these look like. And before, when we graphed these, I said, okay, just sketch in your branches. But here's my question. How do you know if this branch is like really wide like this, or maybe it's really narrow like this? How are we going to tell? Well, I'm going to show you how we're going to tell. Go ahead. Well, that will be part of it, but it's not even, that would still be kind of hard to tell. Knowing where the foci are, it would be kind of difficult to tell how narrow or wide it's going to be. But here's what we're going to do. Do you remember when you did the ellipse? When you graphed the ellipse, you used this, right? And you square rooted that to get 2, and that went on the x-axis. Then did you square root this to put it on the y-axis? This is going to help us to see how wide our hyperbola is going to be. So you're going to do the same thing that you did with the ellipse. Go ahead and take the square root of 16 to get 4. And I want you to go ahead and put 4 on your graph. Now, we know that those 2 points are not part of the hyperbola at all, right? Because your hyperbola can't go through those points the way it opens. But they're going to help us get where the hyperbola should go. And here's what you're going to do. You're going to use these 4 points to construct what I call a box. And the way you're going to construct the box is I usually just start at one of the points, and you want to make these in dotted because they're not part of the graph, they're just guidelines, okay? And you're going to go dotted line until you get down to where this point is. And then you're going to go across, so you go through that point. And then you're going to go up through this point. Do you see I'm making a box, a rectangle, using those 4 points? You see how I did that? Now, the reason I did that is because we know that hyperbolas have what kind of lines that go with them? Think about when we did the inverse variation graphs, because those were hyperbolas. They did have axes of symmetry, but they had asymptotes, didn't they? They had lines that they got closer and closer to but never touched. Before, when we graphed them, they happened to be the x and the y axis, unless we moved them left, right, up, or down, but they were always a horizontal and a vertical line. Well, now they're not horizontal and vertical anymore. Now they're at some kind of an angle. They're at a slope. To figure out what that slope is, we use the rectangle. It turns out that the asymptotes are generated by drawing 2 diagonal lines through this rectangle going from corner to corner. So, using dotted lines, because they're asymptotes, you want to go from one corner to the other, passing right through the center point. And then you want to extend that dotted line outside the rectangle because that's where your hyperbola is going to happen. So there's one of my asymptotes right there. Do you see where the other one's going to go? Draw on the other diagonal. So corner to corner, just like this. Make sure you extend it outside the rectangle, outside the box. Okay. Now, the hyperbola, when you go to draw it, is completely outside the rectangle except for the 2 vertex points that you see in green. Okay? But otherwise it doesn't touch the rectangle and it doesn't touch the asymptotes, but it gets closer and closer to it. Actually looks pretty wide. Whoa. And then this branch comes down over here, something like that. Now we do the same thing over here. Comes up like that, and then down like that. It's because I had my box was kind of stretched out vertically, so that makes my hyperbola very wide. Now, if I had just switched this around and made it 4y squared minus 16x squared is equal to 64. If I graphed this one and did all the same things, I'd divide by 64 again, wouldn't I? And I would get y squared over 16 minus x squared over 4 is equal to 1. Now, which way would this hyperbola open? Up and down, wouldn't it? Because the y squared is positive. You're going to do the same thing. You're going to go up 4 and down 4. Then, to make your box, you're going to put on the other 2 points by going left and right 2. And if you go left and right 2, won't it make the very exact same box? But now this time when you draw the hyperbola, you're going to draw it opening up and down. How are its branches going to be very different than these ones? Besides going up and down, they're also going to be very narrow. Okay, it's going to be a lot narrower when you draw that one. So do you see how that rectangle can help dictate whether or not it's wide or it's narrow? Yeah, you see that? Okay, yes.
So basically, if the y term is the y fraction supposed to go up and down, and if the x term is supposed to go
Yes, if you put it in that order so that when the y squared term is first, it's also positive. It's not always written that way. Sometimes you'll have that y squared term first, and it will be negative. So if you rewrite it so that the positive term is always first, then what you said is correct. If the positive term is first and it's the x squared that's coming first, then it's sideways. If the positive term is first and it's the y squared, then it's up and down. Okay? All right, any other questions on that? Okay, let's see if we can find the foci back for this original one. I think this equation is a little bit easier because it's just a squared plus b squared. So in this case, it's just going to be what? 4 plus 16, right? So 20. That's what c squared is. Therefore, c is 2 root 5 plus or minus, right? So if we wanted to write the coordinates of our foci, the foci are on which axis, the x or the y? The x, so it's going to be plus or minus 2 root 5, comma, 0. Okay? Any questions on that? Because they have to be kind of on the inside of the branches. It's on the same axis as your 2 vertice points. Okay? Yes? You can put them in there if you want. You could probably get a decimal approximation for that and just put a little dot there. Any other questions? Okay? Let's look at this one. It says, write the equation of a hyperbola with foci at plus and minus 10, 0, and vertices at plus and minus 8, 0. Now, I really think it's imperative to sketch a little picture when you go to do these. Okay? This hyperbola is going to be centered at the origin. It didn't specify that, but let's assume that it's centered at the origin. And let's just sketch a quick little graph. So the foci are at plus and minus 10, 0. And the vertices are at plus and minus 8, 0. Okay, so how must this hyperbola open? Sideways, right? Because it's crossing the x-axis. So one branch is over here and the other one is over here. Okay? Now, if it's going sideways, which variable is the positive one? Oh, question? X squared. So here's what I'm going to start by doing. I'm going to say x squared over, I'm going to leave it blank for a minute, minus y squared over, I'm going to leave it blank, is equal to 1. Now, one of these two you can fill in already. Which one? Stephanie? Is 64 under the x squared because this is your a value right there. From the center to the vertex is a. Okay? And it's a because you're working on the x-axis. So 64 goes right here. Now, do I know how far up I had to go or how far down I had to go to make that box? No. So what do I have to use? That c squared equation, which is c squared is equal to a squared plus b squared. Well, c in this case is 10, so c squared is 100. A squared is, you already told me. So the question is, what must b squared be? 36, right? So that's what's going to go right there. And there's your equation. Any questions on that? Okay, I can either do one more example or you can start your assignment. I'm going to start your assignment and see if you have any questions. Okay. So here it is, 1 through 27, the left-hand column. and 5, 29, and 41 through 43.